Let us consider the x coordinate, y coordinate and z coordinate of the rectangular coordinate system. These three coordinates are normal to one another. We consider a three-dimensional point in the rectangular coordinate system. We can draw this point in the rectangular coordinate system if x, y and z coordinate of the point are known. So if x, y and z coordinate of the point are known, we consider the x coordinate of this point along x-axis, the y coordinate of this point parallel to y-axis, and z coordinate of this point parallel to z-axis. And we reach this point with the help of rectangular coordinates. There is x, y and z coordinates. Similarly, we can consider the same point in the cylindrical coordinate system. In order to consider the same point in the cylindrical coordinate system, we need to know rho, phi and z coordinate of this point. So if we know these three coordinates, we can draw the same point P in the cylindrical coordinate system as well. So first of all, we draw this radial line rho in the z is equal to 0 plane such that this line makes an angle of phi with respect to x-axis. So we draw this radial line rho in the z is equal to 0 plane, and this line makes an angle of phi with respect to x-axis. And then we draw another line parallel to z-axis such that the length of this line is equal to the z coordinate of the point under observation, and we get the same point which is in the cylindrical coordinate system now. So as far as the location of rho in z is equal to 0 plane is concerned, the location of rho in z is equal to 0 plane depends upon this angle which is represented by phi. So if phi is 0, rho will be along x-axis. If phi is 90 degree, rho will be along y-axis, and so on. Now, if we look at the diagram, let's say this is the z coordinate of the point under observation. I am talking about this coordinate. Let's say this is the z coordinate of the point under observation, and this line, you see this line represents rho as well. Let me draw this point once again. I am talking about this line, so this line represents rho as well. So anyhow, this is how we draw the same point in the cylindrical coordinate system. And there are three coordinates of the same point in the spherical coordinate system. The three spherical coordinates of this point will be represented by r, theta and phi. Okay, so let us talk about the spherical coordinates of the same point. We can represent the same point with the help of r, theta and phi in the three-dimensional space, and these three coordinates are known as the spherical coordinates of this point. So you see, if we connect these 2 points, this radial line will be represented by r, and the angle of this radial line r with respect to z axis will be represented by theta. So basically we connect this point to the origin of the rectangular coordinate system, and this red line is represented by r, and the angle of this line with respect to z axis is represented by theta. So let me consider this radial line rho once again, and we will consider this radial line rho along y-axis, and if rho is along y-axis, then phi will be equal to 90 degree. We consider y coordinate of the rectangular coordinate system. Here is the y coordinate of the rectangular coordinate system. Here is the z coordinate of the rectangular coordinate system. Let's say phi is 90 degree. So if phi is 90 degree, rho will be along y-axis. So we draw this radial line rho in the z is equal to 0 plane along y-axis. Why? Because phi in this particular case is 90 degree. And then we draw another line parallel to z-axis such that the length of this line is equal to the z coordinate of the point under observation. So we get this particular point, and this point is in terms of rho, phi and z. Then we connect this point to this point, and this line is represented by r, and you see r makes an angle theta with respect to z axis. So basically we can consider this right angle triangle over here. If we consider this right angle triangle, then r will be equal to then rho will be equal to r sine theta, and z will be equal to r cos theta. Z will be equal to r cos theta. So you see, it's pretty clear from this diagram that rho is equal to r sine theta, and z is equal to r cos theta. So if r is known, theta is known, and phi is known, we can draw the same point with the help of these three coordinates as well. You see, we draw this line in the z is equal to 0 plane. The length of this line is r sine theta, and this line makes an angle of phi with respect to x-axis. And then we draw another line parallel to z-axis such that the length of this line is equal to r cos theta, and this line is parallel to z-axis, and we reach the same point, which is P, and now this P is in terms of r theta and phi. So anyhow, rho is always equal to r sine theta, and z is always equal to r cos theta. So if we know r theta and phi, we can calculate rho. Rho will be equal to r sine theta. We know that rho is a radial line which is in the z is equal to 0 plane, and this line makes an angle of phi with respect to x-axis. And if we know r theta, we can calculate z is equal to r cos theta as well. So we can consider the same point in terms of r, theta and phi as well. You see, we draw a line in the z is equal to 0 plane such that the length of this line is equal to r sine theta, and this line makes an angle of phi with respect to x-axis. Then we draw another line parallel to z-axis such that the length of this line is equal to r cos theta, and we reach the same point which is P in terms of r, theta and phi. So you see, what we do, we draw a line in the z is equal to 0 plane such that the length of this line is r sine theta, and this line makes an angle of phi with respect to x-axis. And then we draw another line which is parallel to z-axis, and the length of this line is r cos theta, and thus we draw this point P, and this point is in the spherical coordinate system now, and this point is in terms of r, theta and phi. So let me explain this point once again. In order to consider this point in the spherical coordinate system, we draw a line in the z is equal to 0 plane such that the length of this line is r sine theta, and this line makes an angle of phi with respect to x-axis. And then we draw another line which is parallel to z-axis, and the length of this line is r cos theta, and with the help of these two lines we get this point P which is in the spherical coordinate system. So we consider this line which is represented by r, and you see this line makes an angle theta with respect to z-axis. So you see r makes an angle theta with respect to z-axis. So you see we can find out the location of a three-dimensional point in the three-dimensional space if r, theta and phi are known. You see, if this point is in the spherical coordinate system, and if it is difficult for you guys to consider this point in the spherical coordinate system, then you guys can find out the x coordinate of this point, y coordinate of this point, z coordinate of this point, and you guys can consider the same point in the rectangular coordinate system. It is very simple to draw this point in the rectangular coordinate system. So if you guys want to represent the same point in the rectangular coordinate system, you guys will have to calculate the x coordinate of this point, the y coordinate of this point, and the z coordinate of this point. So let us talk about the transformation of this point from the spherical coordinate system into rectangular coordinate system. So we need to calculate x in terms of r, theta and phi. How do we calculate x in terms of r, theta and phi? So we consider this particular equation first. We know that x is equal to rho cos phi. We know this particular equation, and we also know that rho is equal to r sine theta. So we put the value of rho in this particular equation. So x will be equal to r sine theta cos phi. So we calculate x with the help of this particular equation. So if r is known, theta is known and phi is known, you guys can calculate the x coordinate of this point in terms of r, theta and phi. How do we calculate y coordinate of this point? So we know that y is equal to rho sine phi, and rho is equal to r sine theta. So we put the value of rho in the first equation, so we get this particular equation: y is equal to r sine theta sine phi. So we calculate y in terms of r, theta and phi as well. So y will be equal to r sine theta sine phi, and we already know that z is equal to r cos theta. So this is how we calculate x, y and z coordinate of this point, and we can draw the same point with the help of these rectangular coordinates. Well, if these rectangular coordinates of the point are known, and if you guys want to draw the same point in the spherical coordinate system, then you guys will have to calculate r, theta and phi. So how do we calculate r, theta and phi in terms of x, y and z? So let us talk about the calculation of r, theta and phi in terms of x, y, z. So basically we are going to talk about the transformation of a point from the rectangular coordinate system into the spherical coordinate system. So what we do, we consider the equation for x. Here is the equation for x. X is equal to r sine theta cos phi, and we square this equation. So if we square this equation, x square is equal to r square sine square theta cos square phi, and then we square equation number 24. So y square will be equal to r square sine square theta sine square phi. So we add these two equations, and the addition of these two equations results in x square plus y square, which is equal to r square sine square theta. So we consider equation number 26, which is equal to x square plus y square, which is equal to r square sine square theta, and now we take the square of this particular equation. So z square will be equal to r square cos square theta. So we consider these two equations now. X square plus y square is equal to r square sine square theta, and z square is equal to r square cos square theta. We add these two equations, and the addition of these two equations results in r square, which is equal to x square plus y square plus z square, and we can calculate r with the help of equation number 27. R will be equal to under root x square plus y square plus z square. So if x, y and z are known, we can calculate r with the help of equation number 27. We already know the equation for phi. So phi will be equal to tangent inverse y by x, and as z is equal to, we know that z is equal to r cos theta. So we can calculate theta from this particular equation. Definitely theta will be equal to cos inverse z by r. So you see, we can calculate r in terms of x, y, z. We can calculate phi in terms of x, y, z, and we can calculate theta in terms of x, y, z. So if x, y, z are known, you guys can calculate r, theta and phi, and you guys can consider the same point in our three-dimensional space with the help of these three spherical coordinates. So this is how we transform a point from the rectangular coordinate system into spherical coordinate system, and from the spherical coordinate system into a rectangular coordinate system. If you guys want to represent the same point in the rectangular coordinate system, you guys need to know x, y, and z coordinate of this point. And if you guys want to represent the same point in the spherical coordinate system, then you guys need to know r, theta, and phi of this point, and you know how to calculate r, theta, and phi in terms of x, y, z. Now we talk about the unit vectors of the spherical coordinate system. So there are three unit vectors in the spherical coordinate system. These three unit vectors are represented by ar, a theta, and a phi. So there are three unit vectors in the spherical coordinate system. They are represented by ar, a phi, and a theta. You guys need to know the location of these three unit vectors. So these three unit vectors are mutually orthogonal. They are perpendicular to one another. They are normal to one another. There is an angle of 90 degree between these two unit vectors. There is an angle of 90 degree between these two unit vectors, and there is an angle of 90 degree between these two vectors. So these three unit vectors are perpendicular to one another. They are normal to one another. So this unit vector is along the radial line r, and it makes an angle theta with respect to z-axis. In order to find out the location of this unit vector, you guys need to locate the radial line r first. So we know that the radial line r makes an angle theta with respect to z-axis, and this unit vector will be along this radial line r. So ar is always along the radial line r, and this unit vector makes an angle theta with respect to z-axis. Now we have already explained this unit vector a phi in the cylindrical coordinate system. We know that this unit vector a phi is in the z is equal to 0 plane. So the unit vector a phi is in the z is equal to 0 plane, and this unit vector makes an angle of 90 plus phi with respect to x-axis. So you guys will have to consider the unit vector a phi in the z is equal to 0 plane, and this unit vector will make an angle of 90 plus phi with respect to x-axis. So you know the location of the two unit vectors. The unit vector ar will be along the radial line r. This unit vector will make an angle theta with respect to z-axis. The unit vector a phi will be in the z is equal to 0 plane. This unit vector will make an angle of 90 plus phi with respect to x-axis, and then the third unit vector a theta will be normal to the plane containing ar and a phi. So this unit vector will be normal to the plane of these two unit vectors. So these three unit vectors are normal to one another. Ar is along the radial line r. This unit vector makes an angle of theta with respect to z-axis. A phi will be in the z is equal to 0 plane, and this unit vector a phi will make an angle of 90 plus phi with respect to x-axis. So you know that if phi is 0, a phi will be along y-axis. If phi is 90 degree, then a phi will be along minus x-axis, and so on. So the location of the unit vector a phi depends upon this angle, which is represented by phi, and then the unit vector a theta will be perpendicular to the plane containing AR and A5. It's very important to know the location of all these three unit vectors in the spherical coordinate system. So let us consider two examples. Okay. We consider these two examples if phi is 0 and theta is 0. So let us consider the location of these three unit vectors if phi is 0 and theta is 0. If phi is 0, you see, if phi is 0, we know that the unit vector a phi makes an angle of 90 plus phi with respect to x-axis. As phi is 0, so definitely a phi will make an angle of 90 degree with respect to x-axis. So a phi will be along y-axis. If phi is 0, the unit vector a phi will be along y-axis. If theta is 0, we know that the unit vector AR makes an angle theta with respect to z-axis. As theta is 0, AR will be along z-axis. So A phi is along y-axis. Why? Because phi is 0. We know that A phi makes an angle of 90 plus phi with respect to x-axis. If theta is 0, then AR will be along z-axis because the unit vector AR makes an angle theta with respect to z-axis. And we know that the third unit vector will be normal to the plane containing a phi and AR. So definitely a theta will be along x-axis. So you see, the location of all these two unit vectors depends upon these two angles. If these two angles are known, you guys can find out the location of these three unit vectors. Okay, let us consider another example. If phi is 90 degree, we know that the unit vector a phi is in the z is equal to 0 plane, and it makes an angle of 90 plus phi with respect to x-axis. As phi is 90 degree, so this angle will become 90 plus 90, which is 180 degree. And definitely the unit vector a phi will make an angle of 180 degree with respect to x-axis. So the unit vector a phi will be along negative x-axis. So the unit vector a phi will be along negative x-axis. And as theta is 0, the unit vector AR will be along z-axis. And the third unit vector will be normal to the plane containing a phi and AR. So the third unit vector a theta will be along y-axis. So AR is along z-axis, a phi is along negative x-axis, and a theta is along y-axis. So you guys can find out, you see, the location of all these three unit vectors if theta and phi are known. You see, AR dot AR will be equal to 1, a phi dot a phi will be equal to 1, a theta dot a theta will be equal to 1. Similarly, AR cross AR will be equal to 0, a phi cross a phi will be equal to 0, a theta cross a theta will be equal to 0. Well, AR cross dot A theta will be equal to 0. AR dot A phi will be equal to 0, and similarly A theta dot A phi will be equal to 0. So this one results in 0, this one results in 0, and this one results in 0. Well, AR cross A theta will be equal to E phi. You guys can find out, you see, the unit vector A phi with the help of right hand rule. Apply the right hand rule and you guys can find out the direction of the resultant unit vector. Similarly, A theta cross A phi will be equal to AR. A phi cross AR will be equal to A theta. We know that A cross B, A cross B is equal to minus B cross A. The cross product does not obey the commutative's law. You guys cannot change the order of the two vectors during the cross product. You see, A cross B will be equal to minus B cross A. So if you change the order of these two unit vector, the resultant unit vector will change. Definitely, A theta cross AR results in minus A phi cross A theta results in minus AR, and AR cross A phi results in minus A theta. A three-dimensional vector in the spherical coordinate system will have three components. It will have a component along the unit vector AR, a component along the unit vector A theta, and a component along the unit vector A phi. So a three-dimensional vector can be resolved into three components in the spherical coordinate system. This vector will have a component in the direction of the unit vector AR, a component in the direction of the unit vector A theta, and a component in the direction of the unit vector A phi. If we add all these three components in accordance with the head to tail rule, the addition of these three components in accordance with the head to tail rule result in this three-dimensional vector, which is represented by A. We talk about the addition of vectors in the spherical coordinate system. In order to add two or more than two vectors in the spherical coordinate system, you guys need to satisfy two conditions for the addition of these two vectors. Theta should be the same for A and B, and similarly phi should be the same for A and B. If we satisfy these two conditions, we can add these two vectors directly in the spherical coordinate system as we did in the rectangular coordinate system. Otherwise, you guys will have to transform these two vectors from the spherical coordinate system into rectangular coordinate system. You guys will have to add these two vectors in the rectangular coordinate system, and you guys will have to transform the resultant vector from the rectangular coordinate system back into the spherical coordinate system, which is a complicated process. So if you want to add these two vectors directly in the spherical coordinate system, we need to satisfy these two conditions. This angle theta should be the same for vector A and B, and similarly this angle phi should be the same for these two vectors A and B. If these two conditions are satisfied, then you guys can add these two vectors directly in the spherical coordinate system. Let me explain these two conditions. You see, if theta is 0, then theta must be 0 for vector A and it must be 0 for vector B. Similarly, if phi is 90 degree, then phi must be equal to 90 degree for vector A and it must be equal to 90 degree for vector B. So we need to satisfy these two conditions. So we add these two vectors, and we know that the addition of two or more than two vectors results in a new vector quantity, and the addition of two or more the addition of two vectors obeys commutative law. We can change the order of these two vectors. The result does not change. So if we add these two vectors, we get the r component of the resultant vector, the component of the resultant vector, which will be in the direction of the unit vector ar, will be equal to ar plus br. The component of the resultant vector, which will be in the direction of a theta, will be equal to a theta plus b theta. The component of the resultant vector, which will be in the direction of the unit vector a phi, will be equal to a phi plus b phi. This is how we add two vectors in the spherical coordinate system. The scalar product of the vectors in the spherical coordinate system. So for the scalar product of the two vectors in the spherical coordinate system, we need to satisfy these two conditions as well. If we want to calculate the scalar product of the two vectors directly in the spherical coordinate system, we consider these two vectors a and b, and for the scalar product we need to satisfy these two conditions. Theta should be the same for vector a and b. If theta is 0 for a, it must be 0 for b. Similarly, phi should be the same for vector a and b. If phi is 0 for a, it must be 0 for b. So if these two conditions are satisfied, you guys can calculate the scalar product of these two vectors directly in the spherical coordinate system as we did in the rectangular coordinate system. Otherwise, you guys are stuck. You guys will have to transform these two vectors from the spherical coordinate system into rectangular coordinate system. You guys will have to calculate the scalar product of these two vectors in the rectangular coordinate system. We know that the scalar product results in a scalar quantity. This scalar product will result in a scalar quantity, and you don't need to transform the result from the rectangular coordinate system back to the spherical coordinate system. Why? Because the scalar product is a number, and the number will remain the same in the rectangular as well as in the spherical coordinate system. So in the scalar product, you guys don't need to transform the result back to the spherical coordinate system. Anyhow, you guys need to satisfy these two conditions. Once these two conditions are satisfied, then we know that the scalar product of two vectors results in a scalar quantity. The scalar product obeys commutative law. So a dot b will be equal to b dot a, and it will be equal to ar into br plus a theta into b theta plus a phi into b phi. You guys will have to satisfy the two conditions first. Okay, let's say that vector b is equal to vector a, right? Then a dot b will be equal to a dot a, and it will be equal to ar into ar plus a theta into a theta plus a phi into a phi. And a dot a will be equal to ar square plus a theta square plus a phi square. So a dot a will be equal to ar square plus a theta square plus a phi square, and this is how we calculate the magnitude of a vector in the in any system. The magnitude of vector a will be equal to under root a dot a, so it will be equal to under root ar square plus a theta square plus a phi square. Okay, so equation number 35 is used to calculate the magnitude of a three-dimensional vector in the spherical coordinate system. The cross product. Well, if you guys want to calculate the cross product of the two vectors in the spherical coordinate system, you guys will have to satisfy these two conditions. Theta should be the same for vector A and vector B, and similarly phi should be the same for vector A and vector B. If these two conditions are satisfied, you guys can calculate the cross product of the two vectors directly in the spherical coordinate system as we did in the rectangular coordinate system. If the two conditions are not satisfied, then you guys will have to transform the two vectors from the spherical coordinate system into rectangular coordinate system. You guys will have to calculate the cross product of the two vectors in the rectangular coordinate system. You guys will have to transform the resultant vector from the rectangular coordinate system back into the spherical coordinate system, which is a very time consuming computation. It will take a lot of time, and it is a very complicated process as well. So we assume that these two conditions are satisfied. If these two conditions are satisfied, we will calculate A cross B with the help of this particular determinant. In the first row of this determinant, we have the unit vector AR, we have the unit vector A theta, we have the unit vector A phi. In the second row, we have the scalar component AR of vector A, the component A theta of vector A, and the component A phi of vector A. Similarly, in the third row of this determinant, we have the R component of B, theta component of B, and phi component of B. We know that A cross B is never equal to B cross A. It is equal to minus B cross A. So you guys can calculate B cross A either with the help of this particular equation, or you guys can use this determinant for the calculation of B cross A. You see, we have the three unit vectors in the first row, AR, A theta, and A phi. Then we consider all the three components of vector B. In the second row, we have BR, B theta, and B phi. We consider all the three components of vector A. In third row, we have AR, A theta, and A phi. We expand this determinant. The expansion of this determinant will result in a new vector, and the expansion of this determinant will result in a new vector as well. So this is how we calculate A cross B, and this is how we calculate B cross A. Right? Now, in the spherical coordinate system, we assume that this three-dimensional space is in the form of a sphere of radius r. So r is the radius of this imaginary sphere, and you see r makes an angle theta with respect to z axis. Let us talk about, you see, the limits of these three coordinates. I mean the limits of r, the limits for theta, and the limits for phi in the spherical coordinate system. So the radius of the imaginary sphere in the spherical coordinate system extends from 0 to infinity. These are the universal limits for this particular coordinate in the spherical coordinate system. R extends from 0 to infinity, theta extends from 0 to pi, and phi extends from 0 to 2 pi, right? So these are the three limits. R, which is the radius of the imaginary sphere in the spherical coordinate system, extends from 0 to infinity. Theta extends from 0 to pi radian, and phi extends from 0 to 2 pi radian So this is how we represent a point in the spherical coordinate system. Then we discussed the unit vectors of the spherical coordinate system. There are 3 unit vectors in the spherical coordinate system. The unit vector AR is always along the radial line R. This unit vector makes an angle theta with respect to z-axis. The unit vector a phi makes an angle of 90 plus phi with respect to x-axis. This unit vector is in the z is equal to 0 plane, and then the unit vector a theta is normal to the plane containing AR and A phi. So we discussed these 3 unit vectors. Then we discuss the scalar product of these 3 unit vectors. I mean AR dot AR results in 1. Similarly, A theta dot A theta results in 1. Similarly, A phi dot A phi results in 1. So we discuss the scalar product of these unit vector, and then we considered this scalar product as well. We know that AR dot A theta results in 0. We know that AR dot A phi results in 0, and we know that A theta dot A phi results in 0. Then we discussed the cross product of the 2 unit vectors. We discussed that AR cross AR results in 0. Similarly, A theta cross A theta results in 0, and A phi cross A phi results in 0. If you guys want to find out the proper direction of the cross product of the 2 unit vectors, the proper direction of the resultant unit vector, in case of this cross product, you guys need to apply the right hand rule. And if you guys remember, I explained the right hand rule in the physical classroom. So you need to know how to apply the right hand rule. In the spherical coordinate system, we assume that this 3-dimensional space is in the form of a sphere of radius r. R is the radius of this imaginary sphere, and this r makes an angle theta with respect to z-axis. So we will have to consider a point inside this sphere. We will have to consider a vector, a 3-dimensional vector inside the sphere in the spherical coordinate system. Thank you so much.